Welcome. This is the third video in the series on quality assurance. In the last video, we went over radiographic testing equipment and discussed how and why the different equipment is used. In this video, we will look at radiographic artifacts and repeat analysis. Let's start our understanding of these concepts with exploring radiographic artifacts. We'll go through an introduction. CR and DR has allowed a reduction in patient dose, increased workflow, and improvements in image quality. Along with differences in efficiency in CR and DR, there are differences in acquisition and processing that can create image artifacts. Each different system, model, and their usage has the prospect for a different manifestation or degree of artifacts, of these artifacts we'll be discussing. Even if the vendors use the physical detector hardware, differences in calibration or image processing may yield different results in risks of artifacts occurring. Okay, so digital radiography artifacts. Some of these concepts will apply to CR and some to DR and some to both as we're going through these. In digital radiography, 4 classes of artifacts can be described. They are image receptors, software, object, and other. We'll start by image receptor or PSP artifacts. That would be considered more like DR or CR artifacts, where of course the PSP is photostimulable phosphor, and that is used in the CR technology. So image receptor artifacts. Image receptors can suffer from rough handling, scratches, and dust. Artifacts produced by dust can be corrected with proper cleaning, unless the dust is in the optics of the CR reader. So in the CR reader, if it's in the optic, which is usually fiber optics, thin glass tubes, it can be cleaned. This will need to be corrected by the engineer if it is. Scratches or substantial malfunction of pixels will require replacement of a PSP. Ghosting can occur in CR because of incomplete erasure of the previous image. When completely erased, the image should be uniform and free of artifacts, which can be proven by a flat field uniformity test that we talked about in the last video. This is an example of ghosting right here. How there's previous image information with these hard lines right here, and then this line right here. So this area is more black and this area is exposed differently in here. For this image, it might not need to be repeated, but this is a ghosting artifact. Image plate quality control. DR and CR receptors should last for the life of the system. There is no such thing as radiation fatigue of the technology being used too much, and so it won't operate or work properly over time. There's no such thing. Routine QC should include documentation of image frequency, imaging performance, the physical condition of each image receptor. Now let's look at software artifacts. We'll talk about gain calibration artifacts. An irregular pattern may show up due to the anneal effect or other causes. When this pattern is present, a manipulation known as flat fielding is performed. Flat fielding uses software or electronic amplification if it's the DR, and it can also use software if it's an image receptor, to equalize the response of each pixel. If not calibrated correctly, the calibration can be a source of artifact. So it can actually cause artifact, and here's an example of it here. So a way that there can be software artifacts is also as image compression. An image, radiographic image can be 50 megabytes per image. With these parameters, a 4-view mammography study might be 200 megabytes. Because of this, compression techniques are utilized. Compression takes advantage of redundancies in the data, and it's described as either lossless or lossy. Lossless can compress to 10% of the original size, so we can go all the way down to maybe 5 megabytes on these examples, and can be reconstructed to the original image, and is supported in teleradiology. Lossy can be compressed to 1% of the original file size, and data loss can occur. It's supported in teleradiology, but not in computer-aided detection for diagnosing the images with a computer and pointing out things to the radiologist. Lossy is not acceptable for archiving image, so for sending to PACS and things, we don't use the lossy technique of image compression because it can cause artifacting. This is just an example of some image sizes and why compression is necessary, because there's not enough storage for the PACS servers. If we stored the whole image and reconstructing them in the loss list, there should be no artifacting that occurs with that. In the lossy style or technique, programming way of compressing images, there could be artifacting. Okay, we'll talk about object artifacts now. Object artifacts can arise from positioning errors, X-ray beam collimation, and histogram selection. Okay, it can also be caused by objects in the film. And necklace, keys. This is obviously a pelvis view, we would say. We have keys. There's nails, which we assume aren't in the pocket. It's in the thing, so obviously they can't take that out. And EKG leads, all those kind of things, right? So we need to remove objects from the field as much as we can. We'll talk about collimation and partition. So obviously the anatomy can be missed due to collimation or positioning. That's not what we're talking about here. If the X-ray exposure is not properly collimated, sized, and positioned, exposure field recognition errors may occur. So this is what we're talking about, okay? With the software, when the data is being analyzed, errors can occur if we're not properly collimated and sized, and those can lead to histogram errors, which includes signal outside of the exposure field. Collimation is important for patient dose and improved image contrast. Proper collimation has the added value of defining the histogram. If properly collimated, the histogram can be properly analyzed. If you don't know what the histogram is, or you're unaware, there's videos in the playlist on Principles of Radiographic Exposure 2 on this channel about the histogram. We'll continue talking about collimation and partition. When multiple images are on one film, in order for the image histogram to be properly analyzed, the collimated field should consist of 4 distinct collimated margins. In CR, when we're using a cassette, a PSP, right, you can take multiple images. They don't get analyzed until you put it into the reader. So you can take multiple images on one film. The software can have a hard time distinguishing the edge of one image from the other, and it can cause like cropping artifacts. And this is an example right here with this wrist. There's 2 images of the wrist on here, and it included this area. It wasn't able to just include the imaged field right here. So all this would be included with the digital imaging processing steps, all this data, and it's going to misrepresent the images here. This is an example of the edge, how if it goes off the edge, okay, or an alignment error where we're misaligned here with the cassette, with the image plate or whatever this happens to be, so it can't find the 4 edges, so it's including this whole field, and it's now using all this extra data, this collimated area, to process the image, and it's going to misrepresent the anatomy here. We can, with post-processing, we can typically on the systems, we can select the area that is intended, that is actually exposed. We can rotate the image and do all these post-processing things, and then we can tell it to reprocess, go through its digital imaging steps, and then the image should be represented clearly. alignment is important for the same reasons as collimation, as we said right here. And this is an example of alignment errors. So one image was trying to be taken and another image was trying to be taken on the same cassette, okay, and they got crossed over here. So we have multiple images. This is one main image, this is another main image, okay. So this is an example of that. So we mentioned it, so we'll go ahead and we'll talk about the histogram artifacts. A histogram is a plot of the frequency of appearance of a given object's characteristic. So it's how many times the digital value occurs on either the PSP or the image receptor. Okay, and then it's going to count up how many times this occurs. Again, this is discussed more in the Principles of Radiographic Exposure 2 playlist, histogram topics. So it uses that data and it expects there to be certain peaks, certain number of peaks of different data. Okay, either there's going to be a lot of whites, there's going to be a lot of blacks, there's going to be one big in the middle, and it's going to use that and it's going to trim all that data. And it's only going to focus on a short range or a shortened range of data, and then during its digital imaging processing steps, it's going to represent that. Now, if we have an extra greater bit of whiteness on the film because of the collimation errors and things like that, and it's trying to include all that area, it's going to have another peak of white that it's not expecting. So it's going to try to compensate for that. Okay, and you can see where that error can come in when the software is trying to compensate for something that it's not expecting to be part of the image. Okay, and all that is based on the image being taken. Okay, there's a thing called a lookup table as well that it's going off of. So it's important that the shape of the histogram is characteristic to each anatomical projection, as we just said. The technologist must select the correct exam and view before the image is required, because each one may be different, even within the same exam or the same body part. This allows the appropriate reconstruction algorithm for the final image. And this is an example of selecting two different images, but exposing the same exact way. So the exposure is the same to both, it's the same patient, but there's two different images selected on the software. So during the reconstruction phases, it handled it differently. This is obviously not very acceptable here because it was expecting to see different data, okay, and it treated it a different way. And this is obviously probably the correct way, I would say. Let's talk about some other artifacts. Plate reader and processing artifacts. Noise created by internal electronics of the CR reader system. So the CR reader can cause noise, the electronics inside. Noise suppression filters are utilized, and they can usually eliminate this problem. But if the electronics are faulty inside, whether they're beyond that suppression technology, then it's going to start causing artifacts to appear. Okay, either visually, where it can grossly be seen, or maybe behind the scenes, and eventually it does become worse. So then parts need to be replaced at that point, and service needs to be called. Increased sensitivity in CR and DR can cause background radiation to cause fog. DR is even more susceptible to background radiation, but it's only acquiring the data during the exposure. So there would have to be a source of radiation occurring during that time. A CR cassette or plate can always pick up radiation. So if it's left out in the room or whatever, it gets exposed to some degree, and then you try to use it again before cleaning it, before erasing it, and it gets used again, it's going to have all that radiation, all that fog source is going to be on there with the image that you're just doing. So it's most likely not going to look good. Backscatter radiation can also be troublesome because of the sensitivity of the IR. Backscatter can cause a phantom image. And this is an example of the phantom image and what backscatter is. So backscatter is where off-focus radiation is hitting a source, and this could have been scattered in the patient too, right? And it comes over here, it still has enough energy to hit the back of the film. So off an obstacle and strikes the back side of the film, it creates a loss of contrast and definition. Okay, the TFTs inside, they pick up the radiation from both ways. Okay, sometimes the way that they manufacture, there's a backing plate of aluminum, or it could be some kind of other material, okay, to prevent this. And this could be in the IR, and it's also in the it could also be in the PSP. And you can see some of the electronic components inside and things of the IR plate, okay, is getting picked up here from backscatter coming back at it. If you ever accidentally take an image with the IR reversed, you'll be able to see the image, but you'll also be able to see all the electronics on the backside of it, okay? With most manufacturers, as far as I have known and seen. Go ahead and we'll look at some other types of artifacts: plate reader artifacts, processing artifacts, exposure artifacts. Also, memory problems, digitization problems, or communication errors can occur. So the exposure index, which is the EI, may not be correctly calculated. This is a tool that is within the X-ray machine, and it communicates with the operator, and it tells us, the radiographer, if we're overexposing or underexposing a patient, and this may not be correctly calculated, so we'll be using, it's displaying wrong, and it's usually a number, okay? So this can occur, so we'll be using the wrong or a poor technique. If a histogram analysis problem has occurred, equalization processing can make light areas, which is something that the software does, can make light areas darker and dark areas lighter than what was intended. So we wanted an area to be dark, to look dark, and it's going to try to make it lighter, trying to equalize the data that's taken in because of a histogram problem. Quantum model causes a grainy appearance, typically with lower mass techniques or just a low technique in general, and this can degrade the quality of the image. This is an exposure artifact. CR readers can skip scan lines, missing pixels, and it can distort the image, just being taken in and read by the laser. Plate reader artifact. Aliasing can occur when not enough samples are taken. The Nyquist frequency states that the sampling frequency must be at least double that of the frequency being sampled. So we have to sample electronically. Could be analog, I guess, but this is all digital. So electronically, we have to sample the frequency that's coming in more than twice of the frequency coming in. And what can occur is the moire or zebra pattern can occur. So we'll talk about the aliasing artifact, which is insufficient sampling. And this example here, it's sampling greater than 2 times the cycle, so it's sampling more than twice for every cycle, and we can digitally represent this analog signal correctly because we're getting enough samples. Here, if we, with this higher frequency, and we sampled the same at the same frequency, then it's not going to represent it. It's going to appear that this curve here, this frequency here, is actually a slower frequency. So with the spatial resolution, spatial frequency of anatomy and things like that, it will be misrepresented on the film, okay? And with, I believe this is with CR readers, this moire artifact can occur right here, okay? Because it wasn't sampled enough, or it wasn't sampled frequently enough. So that's something to know and to keep in mind. So here we go. We got operator error analysis. Heat blur is when a CR is exposed to heat before being processed. So this would be an operator error. If we put the CR, the cassette, near a heat source, it will have something called heat blur. We can have double exposure. We can have an upside down image plate. So instead of the one side of the image plate that's supposed to receive the radiation, it's in the cassette the other way. So the back side is what we're actually exposing directly. And histogram mismatch, as we talked about, can occur. Okay, so this is double exposure film. There's a chest and a baby chest, or a neck and a baby chest on here. Okay, so there's two different images on here, and that's a operator error. Should have been processed in between those. Printer errors can also occur. Printer errors is incorrect density calibration, light leaks, transporter problems, laser misalignment. Printers aren't really used anymore, but if there is still a printer being utilized, these points not being correct can cause issues, and it can cause shading or a Cordier effects. Okay, and this is an MRI image, but this effect can happen where it has these lines in it where it looks like the Cordier, okay, pants, right, which is due to certain printer errors. So we'll look at more digital IR specific artifacts. Tilling artifact, which is where the TFT, each chip, so each DEL, each cell has a slightly different electronic value, leading to slightly different brightnesses values for equal exposure. Equalization or flat field software can usually eliminate this, so each one will represent, each DEL will represent correctly with the same given exposure. So there's a thing called dead pixels where DELs are not sending or receiving information, and the DEL in the matrix of the IR, each electronic component that can, the smallest electronic component that can pick up a signal is a DEL, and that makes a grid, okay, which is like the matrix of the IR. Dead pixel artifacts. We'll talk about that and how to fix them. So dead pixels are corrected for in pre-processing. It can be a single pixel or a row or a column of pixels that aren't being received due to the way that the IRs are built with the address buses and everything. It could be a problem with that, so the whole row isn't receiving the data. It's fixed by interpolation, and this actually occurs all the time, and you don't even recognize it because it's kept to a regulated minimum. If the dead pixels on an IR becomes too great, then it needs to be replaced. I would say it needs to be fixed, but it's usually just fixed by the original equipment manufacturer and sent off, and they'll just, and a new one will just be ordered temporarily, put in place in the facility. So it's being fixed by interpolation. Here's some different examples of interpolation, how they can be used. The blue boxes are the only originally corrected data. So the nearest neighbor technique is one technique, and that just has where the data here, okay, is being corrected by the nearest neighbor. So it has this data, it's just filling in this gap here, okay, these gaps here. We have the data here, it's just making all this 100 with this staircase, so it's just blocking off an area and it's just filling that in, okay? That's the nearest neighbor. The bilinear is a little more robust, and it's taking in multiple groups of data. So if this is the original data, and this is data, and this is missing right here, this is a dead pixel, it's taking the 50 and the 100, it's averaging that, okay? This one, it's averaging all these values right here, and it's getting 125 if we average all these values. This is the 100 right here, which is the missing data. It's averaging these two. So this is going to be a better representation because it's more gradual. The gradient's less sharp. Okay, the change from here to here is probably going to be more accurate when 100's put here than 50, because it's going to go 50 to 150 here to represent the actual data in a correct fashion. We'll look at some other ways, and these become much more robust and much more complicated, and it's kind of beyond what we're interested in for our purposes, okay? But I'll show them to you here. So the nearest neighbor, we can see that this still looks really blocky because it's taking large sections and it's just staircasing them off, so it's making just one pixel, it's making a multiple pixels of the same value. So of course it's going to be stair-steppy, right? This is zooming into this image right here. The bilinear is going to be much more smooth, right? And we know this hatch should be curved and everything, and we can actually see it where it's not just like the edges unknown right here, right? The face is not clear. Here we're getting some more clarity in it. And the Lanczos, I suppose, okay, named after somebody, it's capitalized, is another technique, and mathematically they're beyond what we need to know, but we can see, and there's many other different types that are utilized, but we can see more details here, even compared to the bilinear. And each manufacturer is going to have their own proprietary software. They're probably going to be more similar than different from each other, but they still put in a lot of research on how to interpolate, okay, the data properly. And that's just filling in a pixel slot for the final image. It's fixing, it's for a dead cell, okay, which a del on the IR. So the del on the IR isn't working, okay, right here. There's no data that comes from it. In order to create the image, we're not just going to leave that blank, right? We're going to do the interpolation steps. And a lot of research is done on that for different manufacturers. So we'll talk about some more artifacts, the increased sensitivity to scatter of CR and especially DR technology. In DR, though, a lower mass can be used during exposure due to the high DQE of the IR plates. With this increased sensitivity to scatter, though, we do need to be aware of the Compton effects and how we can clean that up. We can clean it up by proper collimation, not exposing anatomy that doesn't need to be exposed, and by grids. We can clean it up on the backside. So DORT or contrast media can cause speckles on the film. There can be electronic interference, just like that sound right there, electronic interference. So here's an example of electronic interference on a film, on an image. So it looks like more from the left side of the patient here. There was an electrical equipment source, and it caused this to occur, okay? This appearance right here to occur more on the left than the right, so it seems like it was coming from the left. So this is an example of electronic equipment interference. This is gauze that's left in the patient after surgery, okay? The fragmented radiopaque densities represent the surgical gauze right here. So this is a object artifact. Grid lines. So this is what grid lines look like when the angle, when a grid is angled to incorrectly, because grid lines run in a certain direction and you can angle into them a certain way, but if you angle into the other way, they're going to show because the divergence of the beam, okay, they're expecting that the x-rays are going to be coming in a certain way, so the grid lines can show. It can also show if the grid doesn't oscillate properly in the rooms and oscillating buckies. And this looks like the grid line does not move, so this looks like it's the oscillating air. Motion problems can occur, so motion can be a type of artifact, and the best way to reduce motion is to communicate with the patient. There's other ways we can go about it. It's discussed in the Principles of Radiographic 1 playlist on the video of exposure techniques. We talk about ways to control motion, but you can change the technique as well if the patient's just not going to hold still, and that can limit motion on the image. Patient's clothing. So this is again on an object artifact. You can see Iowa right there, right, from the patient's clothing. So we need to remove the clothing. The letters can show up. Sequins, of course, can show up. We know other types of metal belts and bras and earrings and things like this, necklaces and things like that, but also lettering on shirts and things, Okay, so these are things to consider. If the lettering, even if it's not raised and thickened like this probably was, if it's has some kind of shine to it, where there's maybe like some kind of metal that's used on it to make it shiny, or some kind of other material, it's probably going to show up. So a lot of times it's safer just so we don't have to re-expose the patient to remove it. Um, a dust, or is this a B? So it seems like this is probably a B on this image, and this is a CR plate. So a B got in, and when it was exposed, the film was exposed. Okay, it's showing up here because it's inside the cassette. Okay, um, blocking the PSP effects, right? The illumination effects. All right, so let's switch gears and we'll talk about repeat analysis. So we talked about all these reasons why a film may or may not be repeated depending on the severity of the artifacts we just discussed. We may need to repeat the film. So let's talk about a topic, a concept called repeat analysis in radiology. An important aspect of a quality management program is the performance of a reject, retake, or repeat analysis procedure. So a reject is all rejected images, including repeats. So a reject is like the top, okay? Everything that has to be redone is a reject. Repeat is patient images repeated, resulting in additional patient exposure. Now we'll talk about the repeat analysis program. A reject or repeat analysis program, which it can be called RAP, is a systematic process of cataloging rejected images and determining the nature of the repeat so that the repeat images can be minimalized or eliminated in the future. Okay, so it's just a process of figuring out why we're rejecting and repeating images. Okay, and then we can take that and we can the data on why, and we can say, hey, is this an equipment problem? Is it a education problem? Is it a individual problem? Okay, or which that's not the goal of the program, is to point out an individual, and the individual may just need to be educated or shown something that's causing them to repeat. Maybe it's just on one exam or something like that, right? But the RAP program, okay, can identify that and work towards eliminating repeats. So this is the information acquired for an effective repeat analysis program, okay, by this group here. And I'm not going to read through all this, but there's some required fields, okay, and there's some optional ones through here. And this would be in the collecting data process, okay. Repeat analysis provides important data about equipment and accessory performance, departmental procedures, and the skill level of the technical staff, okay, as we talked about. So it could be a departmental procedure, okay, that's causing films to be repeated. Let's talk about some advantages of having a repeat analysis program in place. The main advantages of lower department repeat rates are improved department efficiency, lower department cost, and lower patient doses. Improved department efficiency, so with less repeats, the amount of time of an imaging exam decreases. Patient satisfaction increases because we're getting the exams done quicker. They're getting the results faster. We're not having to reposition them and stuff like that, right? And allows the department to service more patients. Lower department cost. Fewer repeats decreases the cost of labor. Repeats also shortens the tube life, so equipment can wear out quicker because we're doing more images. We're asking more of the equipment than what we should, Lower patient dose. A diagnostic image that is unacceptable results in the patient being re-exposed to radiation. Clearly, right? If we have to redo it because the image is unacceptable, then we're having to dose the patient again. Within the RAP program, there's a thing called causal repeat rate. and the causal just means the cause, right? Like the reason why. So in digital departments with the QC procedures show that positioning is the #1 error in repeat exposures. For repeat analysis, a worksheet is filled out to obtain proper statistical data. So repeat analysis needs to be done. The worksheet should include the procedure performed along with the causes. So this is the causal repeat rate right here, with the causes of rejection. Once the data is being recorded, the causal repeat rate can be determined. So you take all the data and you take the number of repeats for a specific cause, so something like positioning, something like earrings being on, necklace being on, some kind of equipment malfunction. It could be a specific equipment malfunction, right? Things like that, right? So you put each of those in categories. How many times did it occur, right? And then the total number of repeats. So there's 100 repeats. It was, 10 of the repeats was for earrings being left in. Okay, so that would be, if you do this right here, it'd be 10% causal rate for earrings being left in. Okay, for positioning, it might be maybe 60%. Most of the time their positioning's off. They weren't turned enough, this and that, right? This is what an example repeat analysis form may look like. Okay, so you just put the patient ID, the minimum amount of patient information, just so it can be looked up later, the exam that you were doing, and why. Okay, the collimation, all these different things, right? And there could be there could be many different reasons. And then take all this, chest X-ray, chest X-ray, chest X-ray, right? So for the exam, there was 3 times the chest X-ray had to be repeated. Why? 2 times it was for positioning. So that's 66% of the time for positioning, the chest was repeated. The other time was for motion. So that would only be like 33% of the time for motion. That would be the causal repeat rate. That caused 33% of the time was motion. Why we needed to repeat it. And that's pretty straightforward. This is an example of the causal repeat rate. Okay. So let's say there's 185 repeat images for the month overall, and 67, okay, for the specific exam, right, are for positioning errors. So what's the causal repeat rate of this? Okay, we would take the 67, which is the one specific, is the specific reason that the exam was repeated. Okay, how many times? 67 times for positioning, and then over the total, so 197 or 185, and we do this, and we multiply it by 100, we get 36%. So 36% of the time it needed to be repeated for positioning errors. What was the cause? Well, positioning. How much? 36% of the time. That's the point of this. Okay, and we could say that it's the causal error rate of 36% for positioning for whatever exam it happens to be. You do this for each exam. The total repeat rate, so this is different than the causal. The total department repeat rate is determined by this right here, number of repeat images, and then the total number of views taken. Okay, so the total number of views taken for the whole time period, it could be weekly, monthly, whatever. Okay, right? That was taken in the whole department during that time. Okay, it could be 1,000, it could be 5,000. I'm not sure, right? Depends what time frame you're looking at, right? And then the number of repeated images for any reason. Okay, and this will give the total repeat rate. How often are we repeating images? Just in general. Okay, the total repeat rate. Example, okay, 1,160 views were performed. This might be a real life example. And 132 are rejected. So what's the total repeat rate? Okay, well, we're going to take the 132 for the number of repeated images and the total of images of views taken, which was 1,160. And we'll just plug that in right here. Multiply it by 100 to get a percent, and it's going to be 11.4% is the total repeat rate for the whole department during that time, independent of the cause. A total department repeat rate. So many factors influence this rate, such as the quality of the equipment, the competency of the technologist, the patient population can cause that. That's something we haven't talked about that. Data collection method. Okay, so the data, depending on how it's collected, can be misrepresented. Okay. The number of images accepted by the radiologist to diagnose. Okay. So a radiologist could be extra picky, so we have to, so he says, hey, I need this repeated. So boom, there's a repeat right there, right? So the radiologist can play a factor in that too. Data from repeat analysis is used to identify which of these factors is a major contributor to the overall repeat rate. If a piece of equipment is faulty, repeat analysis can be used to justify repair or replacement of the equipment, right? You break it down by room and everything. This room, our repeat rate's way higher than the department. For the whole department, 6%. This room, it's up over 12, 13%. Okay? What's going on here? Right? It may be the equipment. If certain employees demonstrate a high number of repeats, in-service education may be needed. The repeat rates, so these are the criteria set, okay? And whether these are hard fast or they're just should be followed rules, I'm unsure, but repeat rates for radiographic procedures should not exceed 8% for general radiography and 5% for pediatric specific patients, and that's could be plus or minus 2% on these, okay, for the leeway due to data collection errors and stuff like that, right? Okay, you can say, that was, you know, it's 9%, but maybe the data wasn't collected correctly, right? But if you're generally under 8%, you're in a good spot. Okay, your repeat rate is low. For mammography, the repeat rates cannot change by more than plus or minus 2% each quarter. So mammography, they do monitor this much more closely, and this is regulated much more highly. And as far as I know, I believe they have to keep logs and everything of it, and that's a big part of the job description for or workflow in radiography. Any department with repeat rates exceeding 10 to 12% should be seriously examined. Okay, so the recommended, okay, is to keep it under 8%. And if we're getting to 10, 12%, there's maybe a systematic issue, okay, going on where it's just beyond individuals or it's beyond equipment, or maybe it is the equipment in the room that is malfunctioning is the main room that's used at the highest volume. So that would be a serious examination. Man, we really need to look at this, right? A department with repeat rates that is too low may also signal a problem with compliance or acceptance of poor quality images. So we may just be passing everything, right? Or we may not be collecting the data. We may be purposely trying to hide things, right? And stuff like that. So there's an expected amount of minimum repeats that should occur, right? And if it's too low, that can be a indication of, you know, incorrect data collecting, things going on, right? Trying to hide stuff, maybe, perhaps, right? So I hope this video was helpful and that you got something out of it on radiographic image artifacts, and we looked at the concept of repeat analysis, okay?